My name is Yujie, and my co-author Jinwen also comes here. So we are going to co-present our paper, Opportunistic Data Flow Integrities, which is a new security primitive that we designed specifically for lowering real-time performance impacts for real-time cyber-physical system. So as motivation, the real-time CPS are pervasive nowadays, and an example of this system can include self-driving cars, drone, and robotics. However, we all know that CPS are also vulnerable. One of the reasons is because these embedded software are often written in memory-unsafe languages such as C and C++, which can lead to memory safety attack. One powerful way to address this memory safety issue is to use a very strong defense mechanism called data flow integrity, or DFI for short. DFI works by inserting checking code into the program binary to validate the value flow according to a predefined value flow graph. As a result, malicious memory access can be captured and such attacks can be detected. However, as I guess everybody knows here, security often comes across on performance degradations. And previous research has shown that DFI can often incur a high runtime overhead, even up to 200% overhead. So the question is, can we apply DFI to real-time system? To answer these questions, let me first introduce some background on RT systems. The real-time systems can be mainly categorized into three types, including hard, firm, and soft RT systems. In real-time system, the workloads are considered as repeatedly executed real-time tasks for many iterations, and each task are associated with a deadline. In the real world, many safety-critical systems such as aircraft are hard RT systems. And our work focuses on these hard RT systems, and the key difference between hard real-time system and the other tools is the hard real-time system requires each task must finish its execution within its deadline, in any cases, including the worst cases. So in order to theoretically guarantee this property, the real-time system developers measure the worst case execution time, or WSET for short, of a task using a set of techniques including both static path analysis and dynamic time measurement. Then the developers conduct a theoretical real-time schedulability analysis using task WSET deadline and its task model as analysis input to check whether all tasks are theoretically guaranteed to meet their deadlines. I know this introduction may be quite lengthy, so to summarize, there are two takeaway messages. Firstly, real-time schedulability analysis is conducted using WSET of the real-time task. Therefore, secondly, if the task WSET is expanded significantly due to some reason such as there is security mechanism deployed on it, this significantly expanded WSET can make a real-time system unschedulable, which eventually breaking the real-time requirement. With this background in mind, we applied the basic DFI to a CPS platform on 4 different hardware and 17 real-time CPS tasks. Then we measure the new WSET when DFI is deployed on it. And our preliminary measurement result shows DFI can introduce more than 200% WSET overhead. As such high WSET overhead can be unacceptable for real-time CPS because it can cause deadline misses of its real-time task. For example, Autopilot is a drone platform. After applying the DFI on it, the new WSET can exceed the task's original deadline, therefore violate the real-time requirement. So one question is, how can we change this? To answer these questions, we take a closer look at what happens during task executions. So we plot the task execution time distributions of 17 real-time tasks in this figure, and we find out that in practice, the worst case execution scenario may rarely happen. And in fact, the actual running time is often 5 times less than the WSET. This discrepancy between the WSET and its actual running time is called slack in real-time terminologies. In more detail, the WSET can be considered as a reserve time, which is a constant for the worst case. And the actual running time is the actually used computing time for specific task execution iterations. Therefore, the slack can be considered as the wasted computing resources. Since the actual running time can be far less than the W set, as a result, there are a large amount of computational resources being wasted for most execution iterations. And therefore, such wasted computing resources can be used as an opportunity for DFI protection without impacting the W set. Therefore, we can provide security without breaking real-time requirements. In more details, DFI is only deployed when there is slack available. Before we dive into the system design details, we first describe the threat model and our system goals. The threat models follow the same threat models as traditional DFI that targets user space applications. Therefore, it assumes kernel and hardware are trusted and the code injection is prevented. And the system goal in this role is to perform as much as DFI checks with minimal real-time impacts, or in other words, with minimal W set expansion. To achieve this goal, we propose our system Opportunistic DFI, or OPDFI, that conducts security checks opportunistically at slack time. Also using slack for security checks is an attractive idea. We need to tackle a few research questions. Firstly, this slack opportunity needs to be recognized. Secondly, with the recognized slack, this slack needs to be translated to security protection. Finally, the opportunistic DFI needs to be securely enforced at runtime. Therefore, our system contains 3 design components in response to each research questions, including on-the-fly slack estimation, security to slack policy, slack to security policy translations, and runtime enforcement. So for the rest of the system design details, I will hand it to my co-author, Jinwen.
Okay, so first, how should we recognize such slack opportunities at runtime? OPDFI recognizes runtime slack opportunities through 2 stages. First, it constructs the slack timetable at the offline. OPDFI first collects the constraints of each path as the slack timetable index and then calculate the slack time of each path. At the runtime, the input is evaluated on the constraint index of each path, then the corresponding slack time is figured out. However, evaluating the constraints on each path introduces high runtime overhead. To solve this problem, OPDFI selects partial constraints on some paths as the index of the slack timetable. For example, instead of collecting constraints for each path, we use the relaxed constraints and underestimated slack time for both path 1 and path 2. Secondly, based on the observation that the input of the cyber-physical system typically follows specific distributions, OPDFI selects the constraints that are most effective for commonly appearing inputs. After recognizing the slack time opportunities, OPDFI needs to deploy suitable DFI security policies without breaking the real-time constraints. Different from the traditional DFI, OPDFI uses different security policies to dynamically protect different scope of the memory operations at different time. So, how should we guarantee the coherence of different security policies under various slack? OPDFI ensures both spatial and temporal security policy coherences. From spatial perspective, all the dependencies of the protected memory operations are also protected. From temporal perspective, critical data are never being unprotected. With opportunistic DFI security policies, how should we enforce it? As opportunistic DFI introduces security protection degradation because of the partial protection, how should we prevent unchecked code from compromising the protected data? OPDFI enforces different security policies by switching different code versions. treating the memory overhead for real-time performance. To prevent attack from unchecked memory operations, OPDFI sandboxes unchecked memory operations, restricting their modification abilities. To evaluate the effectiveness and efficiency of OPDFI, we implement prototypes and evaluate them on 8 platforms, including 4 real-world platforms and 4 simulation platforms. As OPDFI is probabilistic, thus the first evaluation question is how strong is the security guarantee it can provide on the real-world CPS platforms. To evaluate this, we measure the percentage of the protected security-sensitive memory operations on real-world platforms without breaking the real-time constraints. As we can see in these tables, OPDFI can achieve 95% security-sensitive memory operations coverage with 180% less worst-case external time expansion. Thus, OPDFI can achieve most DFI checks with minimal worst-case external time impact. Additionally, in the worst case, OPDFI provides zero protection under zero slack. So the second evaluation question is how difficult is it for adaptive attackers to trigger vulnerabilities on execution path with zero slack? As a successful exploitation always includes 2 conditions. First, the triggering execution path that has no slack, but with vulnerable function. Second, manipulate the input to exploit the vulnerability in the vulnerable function. Thus, we measure the adaptive attack difficulty by measuring the percentage of the input space that can trigger execution path with security-sensitive function with various slack. As we can see in this figure, the input space triggering path with security-sensitive functions, but with no slack, is less than 0.02% on average. So this demonstrates that attacker has little chance to construct the input that can both entering the path with zero slack and triggering the vulnerability. Thus, the adaptive attackers are difficult under the protection of OPDFI. In summary, we propose a new security primitive, Opportunistic DFI, which performs inline data flow checking using the slack in the real-time system. Second, we implement our prototype on multiple real-world CPS platforms. Third, we evaluate the effectiveness and efficiency of our prototype on 8 real-world CPSs. Our project is open sourced. Thank you. Welcome to any questions.